Alright, I think we will probably get started now. Yes, please. Alright, welcome to the McCarthy Observatory and our second Saturday Stars here on October 11th. It's hopefully a little bit more clear out there than it was earlier. Might be able to see Saturn or some other good stuff up tonight. If not, come back next month and hopefully we'll have more clear sky. My name is Mark Polanski. I am an observatory volunteer specializing in imaging and asteroid observations for somewhere around 13 years. Long before I got involved here, the McCarthy Observatory already had a long-established reputation for high-quality measurements and observations of near-Earth objects. The telescope upgrade last year not only helped us continue that tradition of excellence, but expand upon it in a number of ways. Tonight I thought I'd explain a little more about some of the work we do here when we're not hosting star parties or visitors, mainly how near-Earth objects are discovered and observed. First, we'll need to talk about what a near-Earth object is, or NEO, and why we should care about them. Hint, the dinosaurs didn't. And the Oort cloud at the edge of the solar system. To be considered near-Earth, an object must have an orbit that brings it within 1.3 astronomical units, or AU, of the Sun, with 1 AU being the average distance between the Sun and the Earth. 1.3 AU is about 121 million miles, or 194 million kilometers. While those numbers seem fairly large to us here on Earth, where even the Moon is a mere 239,000 miles away, anything that comes within 1.3 AU of the Sun is worth watching because there's a potential for the object to interact with Earth at some point. Most of these objects have stable orbits, but they can be perturbed or bothered fairly easily. Sometimes all it takes is another large asteroid passing too close by, or the right alignment of the planets, or even a distant passing star to nudge an object just enough to change its orbit. More importantly, some NEOs are classified as PHOs or PHAs, potentially hazardous objects or asteroids. These are objects that don't just come nearby, they get up close and personal. A PHO has a minimum orbit intersection distance, or MOID, of 0.05 AU, about 4 million miles. I really like the word MOID for some reason. MOID basically means the orbit of the object comes very close to Earth's orbit around the Sun. Potentially hazardous objects are also big enough to cause catastrophic damage. They're usually larger than 140 meters, or 459 feet in diameter. On a global scale, that doesn't seem so big. 459 feet is basically the length of the football field behind the observatory. But anything moving around the solar system is going to be going very fast. Physics says kinetic energy is mass times velocity squared, and it's that velocity squared part that gets you. A 459-foot diameter asteroid impacting at orbital velocity has the equivalent energy of about 140 megatons of TNT. To put that into perspective, the most powerful atomic bombs humans have ever created so far have the energy of only 58 megatons of TNT. So, an asteroid the size of a football field has well over double the energy of the biggest atomic bomb. So we really want to know if one of these things is coming for us, so we have the opportunity to try to stop it. Everything's based on mathematical probabilities and statistics, which is normally boring stuff, but it's important in this context. An asteroid or a PHO is considered to be a virtual impactor if the orbit is not constrained to the point of ruling out an Earth impact sometime in the future. There's a lot to unpack there, and I'll get into orbital uncertainty in a little bit. But the gist of it is, a virtual impactor is something that we haven't yet completely ruled out the possibility that it might hit us. Even if it's a 0.0000001% chance of impact in, say, 300 years. In this case, even a 1 in a million chance is worth investigating to rule it out. So why do we care about these things? Again, the impact energy of even the minimum size of PHO is 2 to 3 times that of the most powerful atomic bombs. And that's a small PHO no bigger than a football field. If one of those in 1908, an asteroid of about 30 meters exploded in the air over Tunguska, Russia. Trees were flattened over an 830 square mile patch of a very remote area of Russia. Thankfully, the area was uninhabited, so no known human deaths were recorded. But if that happened over a populated area, it's likely tens of thousands of people would have been killed or seriously injured. Just 13 years ago, February of 2013, an asteroid of about 20 meters in diameter exploded about 19 miles in the air, with the equivalent energy of 500 kilotons of TNT. Thankfully, the explosion happened high enough to limit the direct impact damage. Even 19 miles high, the energy of the shock wave was great enough to shatter glass windows across a wide area of the city of Chelyabinsk in Russia, damaging 7,200 buildings and injuring 1,500 people. Though most of those injuries were from shards of glass flying about, because the shock wave hit several minutes after you saw the explosion in the air, so people were kind of crowded at the windows wondering what this thing in the sky was, and then the shock wave hit and shattered the glass in their face. Not a good time. This could have been so much worse if the detonation occurred any lower in the atmosphere. So these things are real, they do impact Earth, and they can cause real harm to us. It's one of the few natural disasters that we have the technology to potentially do something about it. So how do we find them before they get to us? The simple answer is with sky surveys. Within the last few years, several large-scale survey telescopes have come online. The Catalina Sky Survey, Siding Spring, Pan-STARRS, and Atlas, to name a few. We even have support from above now, with spacecraft like NEOWISE and the Vera C. Rubin Space Telescope helping find new objects from space. On the ground, the telescopes in the surveys are generally very large, 1 meter or greater aperture, with very short focal lengths, meaning a wide field of view. Mount Lemmon Station is one of the workhorses of the Catalina Sky Survey, featuring a 1.5 meter f1.6 reflector, with a field of view wider than 4 full moons' width. For some context, the red box shows about how much of the sky that 1.5 meter telescope on Mount Lemmon can see in one shot. As big and wide as that telescope is, it's still just a small sliver of the sky. There's a great line from the movie Armageddon, where the president questions NASA about why they didn't see this big asteroid coming until it was almost too late. The NASA rep's answer is, "Begging your pardon, sir, but it's a big-ass sky." So what most of the sky surveys do is take images in a grid pattern like this, with each image overlapping slightly to cover as much of the sky as possible in one night. They'll take the first image, move over for the second image, again for the third image, down for the fourth image, cut back over for the fifth, the sixth, and so on, until all 9 images in the grid are complete. And then it'll loop back around to number 1 and start the same grid pattern again. So the camera is looking at the same stars for every grid section. It'll do this pattern at least 3 times, sometimes more. The images from each grid section are then compared to the others from that same section. So this is an example of what one of those grid sections might look like. If we line up the images by the stars and then animate or blink, we can cross-reference the stars in our field of view with known stars from the catalog, a process called plate solving. With the positions of the stars known, we can then measure and triangulate the position of the moving objects relative to the stars. With measured positions of the object and a known time the images were taken, we can then project where we think the thing is going to go to. But space is 3-dimensional. A single observing site only gets a 2-dimensional image of how the object is moving. So we really need a different observing site somewhere else on the Earth to get parallax, or using 2 different lines of sight to measure the distance to something. If both of your eyes are working, you use parallax every single day. To quickly see it, hold one finger in front of your face. Close one eye and look directly at your finger, and then switch eyes. Open the other eye and close the first eye, while continuing to look at your finger. You'll see your finger doesn't move, but the background behind your finger does. That shift in the background is parallax. So now imagine your head is the Earth, and your eyes are different telescopes, and your finger is the asteroid. The background stars will appear to shift. That difference in background stars is what allows us to measure the asteroid's position in 3 dimensions. Every time an object is found in a sky survey, the measurements are sent to the Minor Planet Center. The description on their website sums up nicely what they do. The Minor Planet Center, or MPC, is the single worldwide location for receipt and distribution of positional measurements of minor planets and comets. The MPC is responsible for the identification, designation, and orbit computation for all of these objects. This involves maintaining the master files of observations and orbits, keeping track of the discoverer of each object, and announcing these discoveries to the rest of the world. The MPC operates at the Smithsonian Astrophysical Observatory as an office of the International Astronomical Union. Basically, they are the authority on asteroids, comets, and other natural satellites. All new discoveries are reported here, where an initial orbit is calculated and compared to the orbits of almost 1.5 million known minor planets. If the orbit of the new object doesn't seem to match with anything already known, the details of the discovery are posted to the confirmation page for further analysis and observation. So far, we're closing in on almost 40,000 near-Earth objects discovered to date, with over 2,200 NEOs discovered just this year alone. A lot of these things out there. Quick word on the International Astronomical Union. The important bit for this talk is the IAU assigns observatory codes to organizations who have provided enough quality data to the Minor Planet Center. The codes are a simple method of identifying the location of observers, with precise latitude, longitude, and altitude to help calculate the orbits of these objects. Instead of having to provide long strings of numbers for our location or geographic coordinates, we can just say 932, and they know exactly where we are. This helps tremendously for both generating the star charts and expected positions of these objects as we search for them, and for reporting the data back to the MPC. Jumping back to the asteroids, once the observations of a potentially new object are sent to the Minor Planet Center, the preliminary orbits are published on the confirmation page here. This list is updated constantly throughout the day and night as new observations from sky surveys come in from around the world. The page averages 30 to 35 new objects nightly, with more discovered around the time of the new moon because the sky is much darker. It's called the confirmation page because the things that are listed aren't always new, or they don't always have accurate data, or sometimes they just don't exist at all. The big survey telescopes are casting a wide net looking for things, and occasionally they post false positives. They report on all the things they find, and they rely on other observatories like ours to help follow up. We'll then confirm if the objects exist, and then submit more detailed measurements to help pin down the orbit with greater precision. So what does that look like, or what does that even mean? When an object is discovered, why don't we know exactly where it's going? The original observations are usually enough to calculate a basic orbit. In this simplistic drawing, the gray dots represent the discovery observations, or where the sky survey found the asteroid to be over the course of 3 images. The red arrow shows the orbital trajectory calculated from those observations. They're generally pretty good, but not perfect calculations, especially if they come from an observatory far away to provide good parallax. But even that isn't enough to really pin down the orbit. There's still alternate trajectories that fit the observations. These differences in orbital trajectory have a pretty descriptive name. We call it uncertainty. As more observations come in, especially over longer periods of time, the uncertainty is reduced, but never eliminated. The total number of observations contribute to what we call the arc length, increasing the confidence in the orbit and further reducing uncertainty. When enough confidence is built up in the orbit, if the rock comes back around in 150 years, that very minor uncertainty will have had billions of miles worth of travel to accumulate, and the position could be tens of thousands of miles away from our best calculated trajectory. Tens of thousands of miles isn't much in the context of billions of miles, but it could be the difference between a hit or a miss on Earth, given our planet's only 8,000 miles in diameter. That's why the follow-ups matter, especially for PHAs and really especially for virtual impactors. We want to know exactly where these things are going so we have at least a few decades to prepare for any possible impacts. The other problem is, thanks to the sun, we can only see about half the sky at once. We've discovered several objects only after they whiz past Earth, coming from the direction of the sun. Once they pass into the night, they're very bright because they're usually very close, and very fast-moving, making them really easy to spot. But in essence, Earth has a pretty big blind spot. Case in point, earlier this month, RID 2025 TF flew within 260 miles of Antarctica after coming in from the sun-facing side of Earth. We couldn't see it until it was practically on top of us. That is by far the closest approach of an asteroid that hasn't impacted that we've ever seen. Small objects also tend to be very faint. They can usually only be seen once they reach the inner solar system, and as they get closer to the sun. The closer they get, the more sunlight's reflected towards us, making it more likely to get picked up in a sky survey. So what do we do here at the McCarthy Observatory? We're very active participants in the search and follow-up for asteroids, especially near-Earth objects. On almost every clear night, we're checking the confirmation page, looking for new objects we can see. When we find a good target, we'll set up our camera, point the telescope, and start taking images. When enough images come in, we'll start the stacking and data reduction process using software called Astrometrica. The measuring of astronomical objects is called astrometry, so Astrometrica is a pretty fitting name. If we're satisfied with the data, we'll submit it to the Minor Planet Center. This is more or less what Astrometrica looks like. It involves a fair amount of data entry. The stacking process will pull the exact date, time, and pointing location of the telescope out of the image. We then need to match up the date and time with the predicted location of the object to find the apparent motion. You might notice the stars look elongated or streaked. This is something unique to imaging moving objects. In a regular pretty picture of a galaxy or a nebula, you'll stack many images together to produce a single clear image. These are generally stationary objects, though. You can use the stars in the image as reference points, align all the stars, and your stacked image of a galaxy will look pretty good with nice, sharp stars. In this case, we want the moving asteroid to look good, or at least sharp. So we can feed Astrometrica the apparent speed and angle of the asteroid, and it will shift each image in the stack to match that motion. For this particular image, the asteroid is moving at about 19.2 arcseconds per minute, at an angle of 131 degrees relative to north. This is a stack of 20 images. The first image is stationary, and the remaining 19 images were stacked by shifting each down and to the left at 131 degrees, spaced out to follow that 19.2 arcseconds per minute of motion. The result is the stars will appear to streak at that exact angle at a distance matching the expected travel distance of the asteroid in that time frame. Why do we stack an image? Sometimes if an asteroid's bright enough, we can see it in a single image, usually if it's magnitude 16 or brighter. For anything more faint, stacking really helps it pop out against the background noise. For example, here are 4 single images right out of the camera, aligned to the stars and animated in sequence. There is an asteroid moving here. Does anybody see it? Like up here?
We're like right there.
Yeah, it's just kind of a star wiggling about. It's probably atmosphere. So, how about now? Reference stars and record the data to a log file. When we've done this for at least 3 different image sets, we'll take that log file and send it to the Minor Planet Center. 13 Minor Planet Center electronic circulars, the documents that announce these new objects to the world. We even discovered 4 new objects of our own before the larger sky surveys came online. Asteroid 2008 TC3 was something special. It was the first time a member of the International Asteroid Warning Network, a group dedicated to quickly spreading the word of particularly hazardous asteroids, and making sure resources are available to study them to help assess any threat to Earth. And we're regularly ranked as one of the top 50 observatories for asteroid follow-up observations by the Near-Earth Objects Dynamics Site, or NEODIS, an international collaboration sponsored by the European Space Agency. This past July into August, we were ranked 16th in the world on a list including professional observatories high up on mountaintops. In 2024, the McCarthy Observatory embarked on a campaign to upgrade our telescope and camera, with the goal of setting ourselves up for success into the next 25 years. Thanks to the overwhelming support of the community, we reached our fundraising goal in just a few months, and went to work installing the new equipment. This upgrade has made such a difference in our asteroid observing work. There's a lot I can say about it, but this illustration of the difference in field of view says a lot on its own. For finding and confirming asteroids, this is a literal huge upgrade. The original telescope is still a fine instrument, though. The narrower field of view means that finding new objects is more difficult, but following up on known objects is well within its capability. And size-wise, the 16-inch scope still has plenty of light-gathering power to see objects out to about 20th magnitude. To that end, we started looking at possibilities for using the old telescope as a dedicated near-Earth object research instrument. Earlier in the year, an opportunity came up to apply for a Planetary Society Shoemaker grant for near-Earth object research. Our submission requested funding to build a second, smaller observatory dome to house the original telescope as a remotely operable observatory dedicated to near-Earth objects. This will help us potentially double our observation output on clear nights, while also allowing NEO work to continue while the main telescope hosts visitors or other research projects. Plans are well underway. The dome is physically here already, and we're hoping to have the necessary building permits soon to complete this project by December. This marks an exciting new chapter for the observatory as we embark on our next 25 years of service to the community. So to summarize, what is an NEO? An NEO is a near-Earth object, an asteroid or comet that comes close enough to Earth's orbit around the Sun. Why do we care? Some NEOs can be potentially hazardous, with the potential to cause big damage on Earth if it hits us. How do we find them? Large, wide-field telescopes are scanning the sky nightly looking for new objects. Who keeps track of all this? The Minor Planet Center is the one-stop shop for all things NEO-related. And what's our role here? We regularly observe and take measurements of new objects, and provide follow-ups of known objects to help reduce uncertainty, especially if an NEO is a PHO, so we know if a PHO will become a potentially impacting terrestrial asteroid. Any questions? Yeah.
Have you ever found like any asteroids or comets from the Oort cloud like passing by Earth before?
Not like super close to Earth, but yeah. I mean, a lot of the comets that do end up coming in are usually coming from the Oort cloud. None have gotten close enough to Earth to be of concern. At least as far as I know, I don't know of any comets that would be considered NEOs, at least off the top of my head. But they're certainly fascinating objects. They're like time capsules preserving the formation of the solar system, so I like to study them whenever they pop up.
How often do these like asteroids usually pass by?
Oh, it varies. It's almost completely random because we have a rough idea of how many of them are out there. I had the number and I forgot to include it in the presentation for some reason, but we have an estimate of how many asteroids we think are out there. We think we've discovered something like 99.1% of the real PHOs, like the big ones, the 140 plus meters.
Really?
But it's a guess because we don't know until we find them.
Wow.
Mark, could you go back to that near miss beginning of this month?
Yeah.
There's nothing at all in the press about this.
Yeah, this was October 1st.
Same day my stepdad was born. But you say it passed within 260 miles of Antarctica.
Yep.
Just for reference, what's the altitude of things like the ISS? How high do they altitude?
The ISS is usually around 350 to 400 miles in altitude. So, yeah, lower than the ISS. I mean, the lowest Earth orbit satellites right now are the Starlink satellites, and they orbit at around 250 kilometers, which is only like 170 or 180 miles, something like that. Yeah.
About what we saw, are there any examples of like asteroid use? Because you showed like asteroids almost doing so, but are there any examples of asteroids actually directly hitting a building in recorded history?
That I don't think so.
Someone actually did get an injury from a small meteorite fragment. It wasn't anything like seriously devastating. It was at most about that big.
Oh, yes.
off the ground.
That actually does remind me. There was a story several years ago of a small meteorite about golf ball size that ended up going through the roof of a house and landing on the bed. And the person came up to go to bed at night and they found this rock in their bed and they're like, "What the heck is this?" And they looked up and saw a hole in the ceiling.
Really?
Yeah.
Was that person in the bed when their bed was?
Oh no, no. It was more of a surprise to just find a hole in the roof and a rock on the bed. But yeah, cars have been hit, but by little small pebbles, like nothing big enough to actually destroy buildings that we know of yet.
You can imagine the insurance claim.
Yeah.
You hit a what?
Great.
You gotta believe me, please.
What?
You have a question?
Yeah. What determines how what like if it's not size like what determines if an asteroid was to like burn up in the atmosphere actually directly?
That is hard to say because the asteroids there's different combinations, there's different classifications of asteroid. Some of them are like metallic, where they're just made of iron. Some of them are just loose collections of pebbles and dust and rock. Some of them are like cometary material, so there's a lot of ice and a lot of other stuff, like very loosely packed dirty snowballs. So we don't know a lot about them unless they get close enough for us to hit them with spectrographs, where we can then analyze meteor, because this was a relatively small one. I want to say the size was like 3 to 4 meters. Like it was not enormous. Like the 20-meter one that hit Tunguska was enough to cause an airburst, and that's why it blew up. That also was not a dense.
Does it, or does it also involve AI?
It's at this point, it's not. I don't know if it's AI specifically, but there is a lot of automation. That's why a lot of the confirmation page is more about determining whether they actually exist or not, because they do post a lot of false positives. They have a lot of automated systems running that analyze these images. So, like, they'll feed the data into a computer. The computer will just look for things that are different between the images, and if it sees something in a regular pattern over multiple images, it'll say, "Hey, this could be something," and then they'll upload it to the confirmation page. So, for the big sky surveys, it's very, very few people are physically involved in watching those images come in. So, a lot of that is scripted. But yeah, AI would be a fantastic use for reducing those false positives and making sure that something's actually coming through. I'd be shocked if right now they're not using it. I just couldn't find any references to it at this point.
What determines like the speed of an asteroid? Because like you said, it was 140 meters. That is like really dangerous for I guess
Yeah,
extinction.
yeah.
But obviously, speed is or velocity is even more faster than
Yeah.
mass for that.
Yep.
calculation. So
A whole lot more speed. So that thing's trajectory now is very different from where it was before it came towards Earth. So that's true of the other 141 million or so near Earth or minor planets out there. All of them are orbiting, doing different things, and all of them are going to have different velocities. So some could be screaming in at 100 kilometers per second, while others could be coming in at 20 kilometers per second. So yeah, I mean that's the other scary part about it is a smaller asteroid could do more damage if it comes in faster, right?
The minimum speed that the impact Earth is the same as the Earth's escape velocity, 25,000 miles an hour or 11.2 kilometers per second. That's the minimum speed.
Yeah, and it only goes up from there, especially if they're interacting like we call Jupiter the garbage collector of the solar system, because it has this massive gravity well that's kind of keeping all those asteroids at bay. Like, it's kind of
Some Trojans too.
yeah. Oh yeah, now there's Trojans. There's I forgot the other side of Jupiter. There's asteroids that are kind of following Jupiter like like a train. All those are interacting, and they're bumping into each other, and two of them bump in at the wrong angle, and now one of them gets ejected towards the inner solar system. Now it's heading towards us. So that's why we always got to keep watching, keep looking.
how often are there like asteroids over like 20 meters?
There's very few that are bigger than 100 kilometers, but there's probably billions that are a meter.
I mean, the other way to think of it is the sizes are likely always evolving, because like these are all leftovers from the formation of the solar system. So we know that they've been floating around for 4.3 billion years or whatever. So all the larger ones have likely either collided with each other and broken apart into smaller ones at this point. So like out in the Kuiper Belt and the Oort Cloud and even in the asteroid belt, like the asteroid belt's not nearly as dense as like what you see in Star Wars. Like that's not what an asteroid belt looks like. Yeah, these things have like hundreds of miles, sometimes thousands of miles between them. But they do interact with each other, and occasionally like two big ones may come together and smash into each other, and that could produce a bunch of smaller ones, right? So any of the larger ones that if we haven't seen at this point are either like way the heck out there, or they might have had interactions and collisions that might have broken them up into smaller pieces.
I heard my question wrong. I meant like
Oh, sorry.
Like how often like asteroids over 20 meters like hit Earth?
Ah,
That's not real often, thank goodness. So, like Mark said, in 1908, Tunguska happened. That was about 30 meters. And then the next biggest one was in 2013, Chelyabinsk, and that was about 20 meters. So it doesn't happen very often, thank goodness.
And they always say Russia.
Yeah, well, Russia's the biggest.
no, it's
country
a
in the
big
world.
landmass. And those are just the ones that we know about because there was evidence, like there was trees left behind that we could see were flattened. Like remember, most of their surface is water,
Yeah.
so anything that impacts over the ocean, we're not going to see or know about because we're not going to see any evidence of it.
We're gonna see like ripples and stuff.
Tell you though, Mark, we more comment than a question. That Tunguska event, remember when I was your guys' age, no one knew what it was. It just knew something had happened in 1908 in Siberia. It wasn't until the 20s that they were able to go and actually investigate it. Until the 60s or 70s, realized it was probably a comet exploding, an airburst set with Tunguska. The scary part, for me, having grown up during the Cold War, is it happened in 1908. And the equivalent to several megatons, up to tens of megatons of explosion. That had happened 50 years later, in the middle of the Cold War.
Oh yeah, yeah, that would have been.
People were made, the buttons that were pressed.
Yep.
Oh,
Yeah.
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 There was another one over the Indian Ocean that if it had happened an hour or so later, would have been right over India. And India and Pakistan
Yeah.
are both nuclear powers.
I didn't include Meteor Crater. Do you know how big that was and when that hit?
Yeah, they think about 50,000 years ago in Arizona,
And that left a
I wanna
crater a
say
mile
that
wide in the
it was-
desert.
they say as big as a school bus, so
Wow.
probably 25 meters, something like that.
The earlier we know about it, the better chance we have of doing something about it. Because if earlier we know about it, the better chance we have of doing something about it. Because if we catch it, like let's say this thing is orbiting in a way that it passes by Earth, say, every 100 years or so, and we catch it on this pass, but we think the next pass it's going to hit us. If we have an opportunity to launch something that we can crash into it and just nudge it even the tiniest bit now, over the course of that 100 years, that tiny little nudge is going to accumulate and could potentially knock it off course. So that's one of the technologies that we have.
As shown by our survey technology.
Yeah, I mean, so of course this was like several million years ago. So like tectonic shifts, and like that's the other problem with Earth is we're tectonically active. So a lot of those early impacts, the evidence kind of gets shuffled around as the tectonic plates on Earth move around. Like the moon is actually a better record of how often.
Explosions used to create like kind of artificial winter.
Ooh, well we know the Chicxulub event was. That was big enough to cause an artificial winter because enough ash was shot up into the atmosphere where it cooled the planet. Like there was a mini ice age because of that. I don't know what the minimum size would be for that.
It was like bigger than Mount Everest or something.
I mean, we know 6 to 9 miles.
Are all in orbit around the sun. So the biggest threat are all in orbit around the sun. So the biggest threat comes from the comets because they're falling towards the sun for a lot longer. So by the time they get past the Earth's orbit, they're going about 70 kilometers per second. They go really fast. They've got more kinetic energy. Whereas just a main belt object that comes close to us will probably be going just the minimum speed of 25,000 miles an hour.
I'm glad you asked about the Raspberry Pi because we use that.
Gravity is due to its gravity, or is it like directly covering it? Gravity is due to its gravity, or is it like directly covering it?
It could be either. I mean, in a lot of cases, it is gravity because, like as small as the moon looks in the sky, it's actually a good size. It's a third of the size of Earth. So they're both pretty good sized gravity wells, kind of tugging on each other. So the interaction of both of them kind of causes this gravitational. The interaction has the potential to alter asteroid trajectories as they come in. I mean, something that's like bullseyeing for us, it's not going to stop it, but it is an extra gravity well to kind of help tug stuff away or tug stuff in a different direction.
Isn't that why the Earth's sphere?
Sorry?
Isn't the moon, like the moon's gravity is the reason that the Earth is like go out?
Yeah, it's an oblate spheroid, I think is the word.
Well, plus its rotation.
Plus the rotation, yeah.
That's
Force.
Yeah, I mean, because Earth has a molten core, like we have our molten iron core. So like the same way the tides happen, all that metal, all that material inside the Earth is going to kind of want to move towards sources of gravity.
That Earth is a sphere, not an oblate.
Well, it's technically it's an oblate spheroid. It's a spheroid. It's not a perfect circle or not a perfect sphere. It is kind of like oddly shaped.
Kind
Yeah,
of like
it's like pulled by
kind
the
of like
moon.
a basketball that's like not fully inflated.
Yeah.
Question, when we put our finger in front of the, our nose like this, why does how is it that the, TV is moving, like, why does, but it looks like the hand is moving?
Yeah, it could go either way. It depends on where your gaze is focused. If you're staring at the TV, you're going to see your finger move. If you're staring at your finger, the TV's going to move.
Yeah, but what's actually, is anything actually moving?
Blinding one eye.
Oh yeah.
For asteroids that like crash into water, wouldn't that be a great big tsunami or something?
Good if it's big enough. Yeah.
Has that like ever happened?
I don't know. Nothing I know of.
I don't think it's, in the
Probably
movies,
the reason that's I've heard of.
Yeah.
Well, take the two events in the last century or so. Tunguska was an airburst.
Yep.
Charlie Binks was an airburst. So they'd be highly likely to cause a tsunami because blowing there, whatnot should impact.
Right. Yeah. Because then it's just the shock wave is impacting the
most
water,
of
which
them
would have.
come apart in the atmosphere.
Yeah, because it's a tremendous amount of kinetic energy, and our atmosphere is really really good at stopping things like that.
Something a bit more.
Right. Once it gets dense enough, once you get like into the troposphere, it's dense enough to stop a lot of things, like space shuttles and things that come back from orbit. Like that's why like any spacecraft that re-enters the atmosphere is going to leave a plasma trail, because it's people say it's the friction in the atmosphere that's causing that plasma. It's not. It's pressure. It's because you're compressing the air so fast at such a high velocity, the air just fuses together and becomes a plasma.
That's why they go quiet for several minutes on the way down.
Unless they have Starlink.
Just in a jet airplane, it's going so fast that it raises the temperature on any surface that's facing the air by 50 degrees Fahrenheit.
Remember the old Concorde supersonic airliner? With the traffic twice the speed of sound at 50,000 feet? The whole airplane extended by the inches. Because of the heat. Then shrunk again on the way down.
It's all science, guys. Just science.
Yeah. All right. Well, thank you all for coming.
No, thank you
Yeah.
for taking the time to help us.
Absolutely. Great questions.
Yeah, good question. You're right.
It's all just physics.
Yeah,
Thank you.
thank you.
I'm interested in working this industry when I
Also,
grow up. That's
how
what my
likely
job
is it
like
to like,
Yeah.
how likely is it to like stop like a dinosaur killing the asteroid?
So, yeah, it's pretty
Dinosaur
cool.
killing would be tough. We'd
Probably,
need.
probably like use some stuff to like
Wow.
get in there and then just have bombs.
Yeah, I mean
Blow it up or
that's
something.
the literal plot of the movie Armageddon, where they
Yeah.
launch up a bunch of oil drillers to the asteroid. They land on the asteroid. They drill a hole and drop a nuke down it to try to split it in half.
I mean, could we like activate the ISS to like move towards it and just slam it?
That might be a good option. Yeah, rather than deorbit it and let it burn up, we can just leave it as a literal giant mass to use for
Yeah.
redirection purposes. Yeah, I mean, so yeah, the options are basically either slam a giant mass into it, which we're kind of limited to what we can launch off
It's
the
like
Earth.
running a cargo boat with like a washing machine.
Right. Or the other option is you tugboat it, where you launch up a spacecraft for the specific purpose of rendezvousing with the asteroid. You basically dock with the asteroid and then have a rocket engine on the back and have it fire to try to push the asteroid away. So that's one of the other options on the
The
table.
simplest thing, if you're accurate enough, is a dense mass at very, very, very high velocity.
Hmm.
K equals half mv squared.
Right. Yeah, that's that velocity that gets you. So
Oh,
yeah.
yes.
So the hope is that we can get it
So-
early enough, or even the most minute of adjustments. If we just give it one of those, in 500 years, that'll push it off by 10,000 miles.
So in that case, then instead of being, an alternative to nuclear weapons, the Rods for God project could just be you slap a rocket engine onto a 10-ton tungsten hole and
And just let it go. Just let it accelerate for as long as possible. Get that velocity up as high as you
For
can.
someone like me, if we can postpone it by 30 years, I'm okay.
Yeah. Yeah, this is going to be your problem to solve in like 10 years.
Yes, thanks.
What would cause something to go like past the
Thank you.
100 kilometer per second?
Thank you
like,
guys so much.
velocity?
Thank you.
Could like asteroids like go past
Thank
that?
you.
Past the what?
Like 100 kilometers a second?
Probably, yeah. Yeah, I mean, we have like the Voyager spacecraft now is a man-made object that's going, I think, past that. I think it's like 120 or 130 kilometers per second now because it's gotten gravity assists. So yeah, any asteroid that comes close to another gravitational body, like if anything swings past Jupiter, if it gets close enough to Jupiter, the closer it gets, the more of a gravitational assist it'll get, and that could accelerate it to ridiculous speeds.
Is it kind of like how like black holes make stuff when they're like their rings go in?
Sort of, yeah. Because black holes are just big, they're giant gravity wells.
Yeah.
So anything that gets caught in it, if something's orbiting a black hole, it's going to be moving pretty quick. But if something just happens to come in and it has a high enough velocity to not get sucked into the black hole, if it were to slingshot around the black hole, it would get a huge boost of
Exactly.
speed.
Yeah, I think I watched a video on that too.
It's like you're falling, and then you miss it, and you
Right.
accelerate as you
Exactly.
fall, and then you miss it, and just
Yeah.
keep going. I think a third sitting.
The third sitting?
What are you having? Well,
If there's enough people. I don't know. We'll see.
I'll leave the chairs up.
I can change it. Oh, yeah. We'll figure it out.
I'm gonna head out soon.
All right. Thank you.
No, thank you. It was really interesting.
Thanks.
You know, Mark, you're talking about the half mv squared. All the formula I learned at high school. I'm still doing that.